Okay, welcome back, module number 7, Signalized intersection modeling. So in this process, we are going through 4 different modules: link-based signal, which is relatively simple, phase-based signal, and also number 3, how to import the standard data input from Synchro to DTI-Lite. And in the last step, we are going to use the QEN application to generate default signal timing data to evaluate the different signal scenarios. So thanks to the University of Maryland, Professor Lei Zhang's research team, we have been working very closely to generate this scenario setup for evaluating different signal set cases. So typically, we have, if you look at this big flowchart, we start with the input scenario setup with a different traffic signal representation, 0, 1, 2, with a different meaning. And we need to prepare the standard data input file, and particularly you need to make sure you have input movement. We have the effective link green time representation, you have movement and input signal. Or if you have a timing, if you use the detailed phase-based timing status, you need to prepare the input timing, and you need to prepare the input timing plan. These are 2 files you should have, and then you run the timing generator, which is produced by Professor Pengfei Li, and then currently is maintained by University of Maryland Lei Zhang's group, to generate the input timing status into the DTA-Lite. So for the input DTA-Lite, for the signal representation, we have 2 methods. Method number 1, a link-based representation. So what we need here is input movement and input signal. For the phase-based representation, what we need here is input movement and also input timing status. This input timing status is generated by timing generator.exe. So all the information can be visualized and added in the NEXTA interface, and then hopefully this will help you to understand how to model and simulate the interesting traffic signal configuration. So in the first step, if you use a link-based traffic signal representation, you have an input node. In this final example, node number 5 is the intersection. And then in this input node configuration, in this input node file, node number 5 has a control type of 5 corresponding to a pre-time signal. Okay. In the input link, you can try to specify the number of left turn lanes in the input link.csv file. And in the input scenario setup, typically you can use either 1 or 2 for the point queue model or the spatial queue model for the signalized intersection. So some users might recall that we have a kinematic wave model. Typically, if you use a kinematic wave model setup, we automatically use the spatial queue for the signalized intersection. If you use a link-based signal representation, we have to use 1 in this colon E in the signal representation model. Okay. And then we need to also check the input movement file. This input movement file is prepared not by the user. So every time when you try to have input node, input link, when the NEXTA interface open up the input node and the input link structure, it will produce the input movement automatically. In this input movement file, as we can see from the slide later on, it has the node ID, upstream node ID, downstream node ID, the left turn type, and also you have the prohibited flag. By 1, you are going to prevent this movement being used. Okay, so in order to just facilitate a very quick analysis, not providing all the detailed phasing information, you can use this input signal.csv. In this input signal.csv file, you can specify the number of phase plan, the phase plan number here, for example 1 and 2 corresponding to different phase implant, and also you can provide the starting time in second, ending time in second for the different phase plan, and then you can provide the 2-node cycle time, the 2-node for this example, because input signal is a link-based input signal representation. So the 2-node is a downstream node of this link, which is node 5 always, and also you can specify the 2-node offset in seconds. So by doing so, you can quickly provide input signal setup, and if you even don't have any information, we are going to utilize your lane capacity to provide a default input signal in the NEXTA interface. And after that, you can run the simulation. And in this step, I want to just make sure you know this particular tool. Go to the menu, to click on the generate default signal. For this 270 example, we can generate all the detailed input signal for the effective green time for different phases based on the lane capacity specified typically in the planning model. But again, this is a quick and a dirty process. I hope the users, when they have time, they should really utilize the NEXTA database or the NEXTA data hub as a way to organize all the related traffic signal information. Okay. Step number 2, or the stage number 2, what we try to have here is a phase-based signal representation in NEXTA or in a DTA light. So again, we need to provide the input node, input link, and we need to provide the movement. We need to provide, in this case, we need to provide a separate traffic signal timing plan file. In this signal timing plan file, you have the intersection ID, timing plan number, and the starting time and the ending time in seconds, and the starting phase for this timing plan for this intersection, and also the global offset corresponding to the global clock. Some users might ask me why you have this input signal versus this input signal timing plan and the input in the timing plan. The reason is by using this phase-based signal representation, you can literally incorporate all the different phases into our structure. So in this input timing.csv file, you have intersection ID, timing plan number, phase number. This is phase number 1, phase number 2. If you use a European Union standard, you can specify the next phase to show that the phase transition sequence during a cycle. You can also use the NEMA standard in the United States. If you put -1 and in the next phase, then we use a NEMA standard to generate the phasing information for DTA light. We have this green duration for each phase and the corresponding movement strings and the movement direction strings, which can provide it and add it in NEXTA interface. In this example, we have 2 phases, phase 1 and phase 2. Okay. After this stage, you can try to utilize the timing generator to generate input timing status file into the NEXTA. And the required file in this input timing generator, in this timing generator.exe is input timing.csv and input signal timing plan. It looks like a little bit complicated, but this whole process is extremely useful for you to understand the detailed modeling step for what is standardized unified data format in the DTA microscopic package. Okay, so let me try to look at the NEXTA interface to visualize those simulation results. Okay, we have the NEXTA being opened here. Okay, we try to open up ODME or just traffic signal representation. So we can have a test case, a small test case here. Network. Okay, on this simplified representation, that's node number, show the node number. Okay, on this segment. So which type of method do we use? You can try to go through this. These are phase-based signal representation. Okay, you can go to this simulation button. Then we know what's the representation method being specified in our data structure. Okay, now you go to the movement layer. Okay, if you click on the movement layer, you can try to see we do display the turning movement in this network setup. You can also use the configuration to display the movement, simulated link counts, simulated turning percentage, and simulated turning delay. All those are processed by the NEXTA interface. And also number of lanes, turning direction, and the turn type. Okay. So under this movement layer, go to this node, right click. You can try to visualize the turning movement structure. On this movement layer, you can try to click on each movement to check the corresponding simulated volume, simulated hourly volume, and the simulated delay in seconds. So if you move from the movement page to the phase page, you can try to generate the corresponding signal timing plans. Okay. So I would like to close this page and utilize a real-life 270 dataset to illustrate the interesting example. So what do we do here is I go to the dataset, and also I go to this traffic signal. Okay, and I go to this signal intersection. Okay, so it spends some time to figure out the location of the traffic signal dataset for 270 dataset provided by the University of Maryland group. So let's try to go to this dataset, 270 network. Okay, we open this network in the NEXTA interface. Okay, this is the realistic dataset we have in the NEXTA interface. And if you go to the traffic signal, one signal we are interested in is a 3335. Go to movement, right click, and then you should be able to go to the phase. And then for the different phase, you can go to phase 1, phase 2, phase 3, phase 4, phase 5, and phase 7, phase 8. And you can try to click on this movement editing mode to add or delete the corresponding link being used in this structure. Okay, you can save the input timing file, and the next time you can try to read the dataset from this interface. So the related signal is this T intersection 3342. Go to movement, right click, view the movement dialog, and you can try to look at the phase and timing plan, phase 1, phase 2, phase 3, and all those detailed information can be automatically also generated in the NEXTA interface. And if you save the information, open the data folder. So in this input timing data, so you have this session ID, intersection ID, phasing, timing, phase number. You can try to change this to -1, make a correction as a NEMA phase, the green duration, the corresponding movement, and information. So one user can try to delete this input timing.csv, which means I don't have any information available, but in my input node, I do a data filter. Okay. We do see we have two nodes being specified as a traffic signal. So in this case, I close this dataset. I reopen this dataset. Okay. In this process, we are going to automatically generate the signal setup. So go through this node again. To find this node quickly, you can always use Control F. For example, 3335. Okay, then we locate to this node easily. Then right click and the facing. So these are the generated default setting by the NEXTA interface. You can save the timing file. And then if you go back to the 270 network, if you go back to input timing, you can see this is the generated input timing data by the NEXTA interface. Okay. The user can further run the executable of timing generator here, timing generator, to provide input timing status file in this format. Let's try to open up this input timing status file. So in the input timing status file, we have movement stream, starting time in seconds, ending time in second, signal status, form node ID, to node ID, and a turn type. So essentially, in this input timing status file, we still literally check for each link, through movement and left hand movement, how the capacity is being closed or opened for different vehicles. Again, we do not model the right hand movement capacity here because the right hand movement capacity is quite complicated and is a little bit beyond the reach of the mesoscopic simulation. So in this process, the user can check the open source code of the DTA line to see how this movement specific timing status been simulated, been generated, and for the advanced users, they can also change the source code in the NEXTA interface to do a more advanced adaptive signal control. Okay. So in the next few slides and also the hands-on exercise, I would like to go through the process of importing signal from the Synchro and mapping the data, and some process for you to understand how the NEXTA interface can be served as a signal interface, signal data hub to exchange the data in between. So what I want to do here is I'm going back to the presentation mode. We have this GUI interface already. Movement, NEXTA interface, doing the editing and the save. And you can add and delete the phase in the current phase. You can add or delete the corresponding movement strings at a different phase. So some users might be confused by how I use two attributes. One is a movement, the other is a movement string for this type of information. The movement string typically is a node number, 1, 2, 3 plus T, which is a little bit small for you to see here. 1, 2, 3 plus T. This is for the intersection number 5. We go from node 1 to node 3 using the through movement. So this is one movement string we have. On the other hand, we also have this movement direction code. This movement direction code will be SBT stands for southbound through. MBT stands for northbound through. These are typically utilized in the NEMA interface. So we have two types of movement. One is a string, the other is a coding, direction code in our NEXTA interface. Okay. So in our simulation setup, we use the signal representation mode number 2. Okay. And then we can try to perform the simulation. The results look like the following: agent-based agent, departure time, ending time, travel time. You can literally check the travel time trajectory of each path of each agent to see how the traffic signal is being taken into account in our simulator. So let me go through this very detailed, extremely detailed input data flow stream, or this data flow chart from NEXTA or from Synchro into the NEXTA and into the DTA light. Thanks to the preparation by Jun Zhao in University of Maryland, he provided a very nice flow chart for us to go through. Step number 1, we explore the data from Synchro to generate the universal phasing, lanes, layout, and timing information. Step number 2, we import the data from Synchro phasing, lanes, and layout into the NEXTA, save it into the standard input node and input link structure. So because we might have a MAME or old DTA line network, we already have a set of input node and input link. So what we need to do here is we need to merge two networks together. So we need to rename the name of input link and input node from the Synchro as input link 2, input node 2, and input timing 2, so that we can try to link those two set of data set together. Step number 3, we need to manually provide the node mapping between two GIS layers, which is a little bit tedious, but we do provide a NEXTA interface for us to merge them easily. I will show you this process in the next few minutes. Step number 4, we run the timing movement generator to generate the new timing mapping, CSV, and then the users can also change the timing information or generate the default timing information in NEXTA, and to manage all the information together. So after this inventory process, you are going to have this complete input timing.csv plus the input signal timing plan for the different time of day plan. We can run the timing generator to further generate the timing status and run the DTA light. The process looks like it's quite complicated, but we are able to address a number of concerns. Number 1 is Synchro and the main DTA line network. Actually, they have totally different coordinate systems. They may have the total different movement configuration. They may have a different coding schema. One is in this layout and lanes and phasing.csv or UTDF format. One is in our much more streamlined data format. So how do they merge together is challenge. But we hope that by merging those information piece by piece, eventually we can encourage a universal signal data format representation for the whole city or for the whole state. So step number 1, we need to prepare the Synchro dataset. You need to open the Synchro, then explore the file to lanes.csv, layout.csv, phasing.csv, and timing.csv in this UTDF format. Here is a corresponding UTDF exporting dialog in Synchro. Okay, we open up this Synchro, we explore the data. The second step, what we need to do here is we need to import the previous Synchro UTDF format into the NEXTA and save them. Okay, open up this dataset, specify the layout.csv, click on OK, then you can try to import this data set in Synchro. So let me try to show you this step later on. I want to go one more step further. You save the project in the same folder, and you will have the same set of input node, input link, and then you need to rename the input node, input link into this version number 2 in this input node -2 or -2 format. Copy them into our old or the main DTA-like network folder. So you will see we have this Synchro network, the main DTA or the old network in DTA-like. We are going to show you a quick process to merge these two networks together. You can go to the layer, reference line. You can use log or unlog interface to move the network very quickly. And then finally, when you try to compare the network, you can zoom in and zoom out. Then you can specify a mapped signal intersection. One is in the old DTA-like format. The other is a Synchro data format. Okay, mapping these two network is not that straightforward, but still is a very useful way for you to construct a universal signal data representation in our mesoscopic simulator. And then finally, we can generate the new timing mapping. And then we can verify the input timing results along this way. Okay. You can also verify the input phasing results using the NEXTA interface, and then finally running the timing generator to generate the input timing.csv and run the input timing generator to generate this input timing status. A lot of terminologies here, but once you're familiar with this process, you will be able to model the traffic signal in mesoscopic traffic simulation open source DTA-like package. So let me try to show you how we can do that step by step. So I have this NEXTA interface. I go to the tool. I go to import Synchro. Okay. I go to the software package. I go to the signal. I go to one of the steps with the data export from Synchro. Okay. So when I go to this particular folder, here is the layout.csv, which is the output of the Synchro. Click on this file. I automatically generate or exported all the information into the NEXTA format. Click on OK. You save the data, and then you go to the file, go to the open project folder. Okay, you can just try to save it again. And then we can have input node. Again, those node ID are in the Synchro node ID system. And the coordinates is also the Synchro coordinate system. And you can also get the input link. And you can also get the input timing. So as you can see, in this input timing.csv, we have the intersection ID, we have timing, we have phase ID. The NEXTA phase ID can be specified as a -1 as a NEMA phase, green duration, movement stream, and the movement direction code. So be careful precisely. So we can try to delete this movement node ID coding fashion, because those node ID eventually will be replaced by the main DTA-like node ID. So what we need here is the movement direction code, is the EBT, MBR, WBR. So the remaining task actually is quite simple. Is this intersection ID, this column here, is specified by this Synchro data format. So what we need to do is we need to build a mapping to change this node number from this Synchro node ID to the DTA-like node ID. By doing so, my NEXTA interface will be able to read this EBT, MBR, WBL, read this directional code and then automatically generate the default signal timing in DTLI format using all the phasing and the green duration and the movement codes. Okay, so let me try to also show you this process. If I go to the step number 2 and then number 3, we go to step number 3. Okay, in this data set, we have input link 2, we have input node, and the input node 2. This input node.csv is a main of the old DTLI format. If you click on this file, they have node ID here will be different from the Synchro data file. This is a Synchro data file. So obviously you can have the different file size. Okay, so let me try to open up this data folder. I close this file, open up this data folder. So when you open up this data folder, as instantly you can see we have two different networks because they have two different coordinate systems. Okay, now you need to go to the reference line to really match these two different networks together. Okay, if you go to the reference line layer, right click, you can unlock the reference network. Okay, now you can try to move this network. So you can see a very nice feature in the NEXTA. We keep the old DTLI network fixed. You can always try to use this menu. You can move the network. You can use the mouse wheel, zoom in and zoom out to resize the reference network from the Synchro. You can do a quick resize here. You can also use the control key to change the vertical, or to use the shift key, shift control, and then to change the size of this network. Then eventually, I don't go into the details with you now. You can try to compare the node number of the two different networks easily. So some users may ask me to have a fully automated process for this mapping function, but we look at the reality. Many networks might have a very different network structure, so we still encourage the users to do this manually to compare. One is a DTA node number, the other is the Synchro node number, so that you can combine these two networks in a much more systematic way, because any error you make in a signal representation might create very unrealistic traffic queue spillback. Okay. So after you have these, we should be able to go back to the signal representation. You should be able to maintain a combined input timing.csv. So this is input timing.csv, and the corresponding input signal timing plan becomes the central pieces for this signal data hub. With these two files, with the help of timing generator exe, you can run this exe. You can just have a very quick run here, and they will generate the input timing status as a result. And this input timing status will tell you for each movement, for the through and the left turn, and how many seconds of the green time at each precise time horizon. Okay. For the information here, I would like to going back to the NEMA structure. If a node is designed or specified as a pre-timed signal, node type number 5, if there's no input timing data available, and the NEXTA will generate the default NEMA phasing as we showed before. Okay, for the two type, one is a standard intersection and a T intersection. And I use some slides from Dr. Milan to show the movement phasing numbering if you are not familiar with the NEMA interface. And the ring barrier structure, in this case, 1, 2, 5, 6 corresponding to different movements, and then we have two barriers. If you calculate the cycle time, 1, 2, 3, 4 corresponds to the two ring structure. And in this case, the phase 2 and 6 has to be ended together so that we can move to the next phase. Session 7.4 is the QEM session. QEM stands for Traffic Signal Quick Estimation Method. This particular Excel application is produced by Professor Milan. Currently, he's assistant professor at the University of Wyoming. You are more than welcome to visit his latest, greatest homepage. And we have a related reference about the signal representation using his Excel spreadsheet. I'm just going through this Excel spreadsheet very quickly. More detail is provided by his paper and Excel package. You have the input interface. You can input for the standard intersection. You can have southbound, northbound. You can specify the speed limit, volume, number of lanes, and then by inputting this data, you can quickly get the movement specific capacity. More importantly, you can try to get the phase designation, like how the dual structure will be generated. This phasing generation is much more advanced than the default data in the NEXTA. So I fully encourage the users to try this on, particularly if you are a planner in this area. So using this QEM application, I provide the slides here. You can create the finite ring structure, and also you can get the corresponding capacity, a lot of information here, and you can get the total cycle time calculated based on the HCM manual. And in the summary sheet, you can have the turning volume, number of lanes, and all the control delay level of service calculated in the setup. So before I move to the next session, I want to demonstrate this QEM session, QEM Excel spreadsheet. So for what we have here, I go to the traffic signal. I go to the QEM diagram, and he has this learning document, the paper, and the QEM user's guide. Okay. Produced, and then for you can go to this QEM Excel spreadsheet, and you can try to punch the number such as the volume 200, try to change the number of lanes 3 or 2, and change the speed limit, say 50 or 40 miles, and then automatically the Excel spreadsheet will do a phasing calculation for you using this dual ring structure. We compare literally the result from this quick analysis Excel spreadsheet. The result is almost 95% consistent with the Synchro result. So I fully encourage the users to try this utility. So all the detail is really in the calculation spreadsheet here. You can try to get the summary spreadsheet in terms of phase designation. So you can get the phase number, split duration. You can get the total cycle here, movement capacity calculated based on the HCM value, V over C ratio, because the capacity will be different, so you will have the different V over C ratio, and the control delay calculated based on the HCM. And finally, you can get an intersection level service, and you can get the different phase timing plan, and you can get the final report just as what you have in the Synchro, and you have layout, lanes, volume, phasing. Those are the standard data format in the universal UTDF format provided by Synchro. So by illustrating this very useful QEM process, we finish up our traffic signal representation in detail line. In summary, here we have input link based representation. We call the input signal. We have a phase-based representation. We call these two essential files as input time mean and the input signal timing plan. Then we use a timing generator to generate input timing status, and the input timing status will be utilized in DTLab package. And then we show a process of how to merge these synchro data step by step, map their timing information locally, map the node correspondence between synchro and the DTLab, and then finally we encourage the users to utilize this phase-based representation as a universal network-wide signal representation for mesoscopic simulator. Thank you.